How does syndrome measurement work in quantum computing? Imagine trying to find out if a delicate glass has cracked without touching it directly. That's similar to what syndrome measurement does in quantum computing. It helps identify errors in qubits without destroying their quantum state. When working with quantum computers, errors can happen due to noise or interference. If we measure a qubit directly, we risk collapsing its superposition, losing the information it holds. To avoid this, syndrome measurement uses a clever trick involving auxiliary qubits called Ancilla qubits. These Ancilla qubits are prepared in specific states and entangled with the main qubits, which contain the quantum data. Through carefully designed quantum circuits, the Ancilla qubits interact with the logical qubits without disturbing their superposition. After this interaction, only the Ancilla qubits are measured. The results of these measurements are called syndromes. They reveal if an error has occurred, what type it is, and where it might be located, all without directly measuring the main qubits. This process relies on stabilizer codes, a framework that keeps certain properties of the quantum state constant unless an error happens. When the Ancilla qubits are measured, the syndromes indicate deviations caused by errors like bit flips or phase flips. Bit flips are when a qubit changes from 0 to 1 or vice versa, while phase flips change the relative phase between states. Sometimes errors involve both, represented by the Pauli-Y operator. Once errors are detected, corrective operations are applied to restore the qubits to their intended states. This process is repeated many times during quantum computations to catch errors early and keep the system stable. Different strategies, like using shear states or Steen states, help improve the fault tolerance of syndrome measurements. These states are special entangled Ancilla states designed to reduce the chance of introducing new errors during measurement. Challenges include maintaining high measurement fidelity of the Ancilla qubits and preventing errors from propagating during the process. Advances in measurement techniques and decoding algorithms are making error detection more accurate and resource efficient. In essence, syndrome measurement works by indirectly gathering error information through Ancilla qubits and stabilizer measurements. This allows quantum error correction codes to identify and fix errors without destroying the fragile quantum information stored in the logical qubits. This step is fundamental for building reliable quantum computers that can perform complex calculations over time.